Morning, guys. It's 2:27 in the morning. I wake up because I figured out, you know, I have an ability to work in my sleep. Literally, it's not a good thing. It's not a good thing because I don't get to sleep ever normally, so I don't get to enjoy sleep as everyone else does. With all that said, I'm smiling because now I can explain this crack. I can explain this crack, and I think I have the whole process. I'm smiling inside. You don't know how good this feels. All right, of course you do. These cracks. Let me do this for you again. These cracks. I'm going crazy trying to make them happen. I even stated that to get these cracks, these cracks are tension cracks and not compressive. How much of that? Because of the shape. And it happened after post-tensioning 2 and 11. 2 and 11. So we assumed, as the CEI did, that it put tension inside 10. And it put tension inside 3. Watch, I'll switch this around and I'm going to tell you it actually put compression in 10 and compression in 3. And how that was resolved was tension cracks. Right, that's crazy shit, right? Watch. Alright, so anybody engineers out there, follow this. It's so simple. Oh, I'm exhausted. So, 11, we know that 11 and 2 were put in compression. That doing so created tension cracks in 10. Don't think of that. We're missing one that I'm smiling because maybe you're caught on now. And I'm delayed a little bit. Oh, I forgot to do my summation. So I'm going to show you pretty much the failure of the structure that I think it's complete at this point. I think the evolution and the revolution is all complete. No kidding. No kidding that it's the end of the story. This is going to turn out to be a longitudinal post-tension elongation miscalculation. LPTEM. Longitudinal post-tension elongation miscalculation. I just coined that real quickly. That's what you get at 2:30 in the morning. Alright, so this happened on 2/28. So how do I get tension cracks and compression? Have you guys figured it out? I just wrote it. This created the force in the structure inside 10 and number 3. Number 3. This created a downward force. Remember though, we have 4 bars in there. 4 bars. I want to make this kind of look pretty, but I can't. Can I? I don't have I don't have something straight right handy. I do have this. I have this old thing here. Something like that. The connections, I'm not sure. This happened to me in the dream, remember? So I don't recall 10 exact setup. So during my sleep dream, my working sleep. So this has these bars in here. This created a downward force in there. These bars are right now hand snug. Remember, like I said on the other ones, when they do the detensioning, I'll get to that. So they're in place. They've got just need to verify that they had these guys on top of there, and I'm sure they did. They had the plates and the nuts on top of number 10. And so when they're just sitting there snug. So when this created that force, it actually put a downward force in the deck. the deck, we should be able to find that the scaffolding deflected in some capacity with these cracks. So this isn't a this is no longer a camber up deal going on here. No. This is actually a force down. When it went down, when it went down into the longitudinal cables, remember there's only D1s installed. D1s could not hold the counter force of this, of 580 kips. D1s could not take, D1s and the transverse cables were, well, specifically the transverse cables were not post-tension yet. So right now, you just have D1 and the canopy tensioned. So to make these cracks, we just need failure in the D1 and D1 and no transverse cables because they weren't done yet. And you can add them back. You can all of a sudden make them appear that they were done beforehand, and even though we see it in the schedule, that it's not done to after the rest of the floor longitudinal post-tension cables are done, then the transverse cables are done. So we're missing transverse cables here. When they post-tension 2 and 11, they only did D1. So this number 10 and number 3 are only pushing down on a deck. Only down a deck with D1 resisting up, or scaffolding also. But only D1 is resisting the downward force up. But D1s are too far apart. They need to transfer the load to D1s. They need the transverse cables. So right now they're doing it with concrete, and they're doing it with the reinforcement. Reinforcement is pretty badass. We know it didn't fail yet. So let's don't kill reinforcement yet. The reinforcement in 10 are the stirrups. So we don't have to kill that yet. We don't have to kill that yet. So this is where the imbalance is. It was able to deflect down here because it had these guys only had D1s up. So only D1s were kicking. D1 and C2 and C4 perhaps. C2 and C4 at the time this was being done. The resistance is not there yet. So now this is the crack I said I've got to be able to figure out every last crack. So this was a deflection down. That deflection down creates this crack right here. I'm going to take liberties and make it larger. Right here. This deflection down creates this crack. This crack would have told you. This crack speaks what's going on here. This crack I only get with this dipping down. You can't get this crack if this deck doesn't go down at this time in this stage of the game either. It's a small crack at this point here and some on the ends. But again, that's because these guys didn't have the transverse cables helping out. As it punched down, or let's call it punching down, I don't want to go down shear punching and all that shearing. I don't want to go down that line. So as it pushed down, this C2 and C4 this one stayed flat. So C2 and C4 had, I think, more capacity to stay flat in the distance than D1 alone. Now I've got to do the math on that. Remember, I woke up with this in my brain. So this is forced down. This creates that deflection here. Now the whole bridge we know through a video, I can tell you through a video, we know where the forces resolve themselves ultimately in the end. We know they resolve themselves somewhere about here and here. The ultimate failure. The ultimate failure is here and here. But I need to just resolve the cracks first. This crack is compressive related from this. It was compression related, shows a deflection in the deck, showing the longitudinal post-tension cables, post-tension, elongation, miscalculation. So now they finished post-tensioning the structure. These cracks, they don't know how they came there. They got to figure them out later, which we're at now, which I think that explains it. They had a schedule still to keep with what you're going to do, not timeline, but scheduling. This was always going to fail. This structure was always going to fail. If you put all of these back in, if you now put the cat back in the bag after this, you now put the transverse cables in. These cracks were never. This was never made whole again. I don't know what the transverse measurements are of these guys, but this required a new calculation for post-tensioning for this guy, because this space, I don't know what the after results are, but they're not to be taken lightly in what's going on here, especially when you start to compress number 10, the 4x4, putting it in compression. These cracks had to be recalculated in there. I don't know how they transverse around number 10. I don't know how much gap they created. Think of it as a cracked window in your house. You may have it cracked only a 1/4 inch, and you have 4 windows cracked a 1/4 inch. That's 1 inch. It does matter. Coming to this corner over here, let's do that real quickly. Let me see if I can zoom in on that. I know I can. Let's get to that corner. Oh, I'm exhausted. I want to sleep. I wish I could sleep. I just got into bed. Probably, I do that. I told you guys I sleep like 10-minute cycles. So all night long, 10 minutes, do. All night long, all the time, ever since I was a kid. Where I was going to burn out, I told you at 25. That's what I calculated. I was obviously wrong, but apparently wrong, right? So here's the pipe. This is not the scale. The scale is off. I've definitely got some liberty issues here. It's down here like this. And here, this would be the pipe through the deck roughly. So I don't want to trash this, but I pretty much can trash it now because it doesn't have any significance to me anymore. This is 10 inches, as I understand. So this is being held on number 10. So let's look at detensioning. So we have this just sitting over there in the staging area. It was worked for 30 days or whatever it might have been, 30 plus days it worked, possibly because they had shimming under there. I'm going over what I went over in previous videos, but this is the cycle of the whole video explaining it. So this had the shimming there. This allowed the transfer of the dead loads of approximately, I'm just taking liberty for sure, because I don't know how much this overhang could, from here downwards. From here downwards. This is the dead load force, but remember 12, I'm going to now do it for you. This is 12. 12 has 2 components to it, the outside 10 inch and the internal measurement of this. I think it's 3 foot, I don't recall, 3'3". So it's more of it onto the deck than not on the deck. The part that's not on the deck, remember, it's not shimmed, so those loads all transfer back to the deck. If we look at it as a dead load calculation, and also look at it at the back end of this way of my where am I going? No, sorry guys. So I have to do. I want you to see both at the same time. Oh, and you couldn't see the top. I apologize. Let me go out. I'll go over that point again. Right. So what I did is I drew a line down here. I blue inked it here and here, saying this is the dead load. This section here, dead load of the weight of this of the canopy. Also, this is number 12. This is the dead load. I stated how 10 inches on the outside of this is unsupported. It's not shimmed. So all of that load of the column, the 10 inches, comes back onto the deck. This makes it the most weight, theoretical weight, at the very edge of the deck, which is here. So this point here is the concentrated load with this column the weakest point is here. That weakest point at the back of this 12 is here. So this point, as you look at it this way, is here and here. You can see that that is, oh I'm sorry, inbound, that is your shear plane also. So the OSHA report, if they went down it, this can explain these cracks better than the way, you know, I hate to attack the OSHA guy because I'm in that report. So, but it's just so simple. I mean, come on, let's give everybody a break here. I'm the only nut job that's got this many crazy hours and is consumed by this thing. So, even with my limited, let me try to make sure that's over. Yeah. Even with my limited access to data, I can explain it this way. I'm not bragging. I'm just saying that I'm not blaming OSHA because I'm sure the OSHA guy had other jobs to do, not just be consumed by this product here. So here's everything. So here's the dead load of this on top of here, being held onto this deck. This being in shear, wanting to fall off. So this cross section here, I'm going to draw it in orange ink. This cross section here, we know failed, and it's right above number 11, which is really back here. So here's 12, the line coming down. So this is really back here, not there. So the cross section that failed is the top of here, and it comes down slightly. Let's see, I've got to get above the pipe. It's above the pipe and across the pipe, sort of like this path here. That leaves, if you look at it, that leaves, I'm going to use black ink. That leaves the cross section. Let's look at the cross section, what's left. And now I'm going to go back to the orange ink to continue my shear path with orange ink. If the loads are coming down 12, shear is typical on a 45. So let's do 45 coming back into the deck. But what I want you to take note is what's left. This section here is what's left. Don't think about what you saw, think about what was left, or what's remaining. And you see now this is a wedge. This wedge has number B. I call this one B. Now it's A or it's B. I call this one B, and this was A. So B has a 288,000 pounds of force applied to it during transportation and also while sitting in the staging area. I believe in the staging area they did not detension A and B to show what it would look like over here. In the staging area, maybe they did not have shims under there. That would be nice to know, and maybe they didn't. But either way, if it didn't exhibit those cracks we saw, OSHA reported right here, then that means this was being held up by B for sure. If they had shims there, then it still means B and the shims, the formwork, was holding up 12, this dead load section here. When they placed it at the location, they released B. They released 288,000 pounds of force. They released it. B, upon being released, has this weight that it was being countered by two things possibly in the staging area. One are the shims, that might be the formwork, which have been formwork then, and the clamp force. So now we don't have the shims any longer, so that means all of 10 is now an overhang. It's an overhang. It's like holding, you do the math, that's 13 feet by whatever, that's 1,000, 2,000. It's probably only close to about 3,500 pounds out here. If I do the math right, is it 2 foot wide? It's probably only around 3,500 pounds for you guys. It's not quite a ton, but it's close. That's my rough calculation. Here's the thing about what I just said though. I have to deduct. For 10 has, I'm referring to it as I like their term blister. I'm going to refer to 10, base of 10 as a blister. Watch the deck. I'm going to come across here. Because this blister is where it's anchored in. Number B is anchored through. Because this was put on the bridge. This was put on the bridge on the deck afterwards. So this was poured along with this blister. This is where the anchoring is. This was wet. This was set in hard set in concrete. This was hard set in concrete with duct around it. In this configuration. Now I would hope that this is straight. I assume that this is straight. Any bending or profiling of this B, well, that even works against it even more. You just want this to be straight shot. Let's assume it's 38 degrees, whatever this is supposed to be, I forget. 38.1, 33.1, 38.7, 9-12. Okay. So this is just sitting on the deck. So you see the profile there now expands out to here. Because I have here, remember? I'm going to recapture that. That now means that the shear doesn't say, well, concrete's here, I'm coming back to this direction, this way. It can, I just can't, that would be like a cantilever now, kind of like a weird thing, but I can do shear two ways with this. Let me just do it imaginarily out here. The forces are still out here, and it's more compressive down here. If it's more compressive down here, shear still has to, I mean, I've never seen something like this. Still has to find a balance. So if it's got shear up here at this point, just by where it sits on the deck in the dead load, where is it here? Is it here with no supports? Or does the weight of this transfer down that 10 blister and it's actually down here? You see that? Is it down here now? And also, watch where I do the base, in here, at the base. This explains at the bottom here, if we look at the bottom of, shit me, oh, I thought I couldn't see it. At the bottom of this girder I call it a diaphragm girder, it's undercut. It's undercut, and it's kind of a weird, it's undercut, and that undercut, to me, could be also a transfer of the shear of it being at the base there, resolving itself just a few inches above, the shear just a few inches above, starting above. Shear doesn't always start where the tip of things, it starts, below the surface. So below the surface here gives you a nice cutaway. If we follow 12 straight down now into the deck, the loads of it, that lines up with that, this A, pulling forces that way. A pulling forces that way, theoretically, it's 288,000 pounds upon that plate. 288,000 pounds of force has a shear going plane itself. And let's go that way with it. And I'm going to mess this up. Let's go this way. So this creates that wedge we see. If I come this way with the shear plane, when we look at, I said it has a drop off in part of my videos. When we look at the OSHA report, we see the plane of the top of where 11 was.